Good morning to all. I am Dr.S.V.Mahesh Kumar, Associate Professor, Department of ECE, Bharat Institute of Higher Education and Research. Today we are going to discuss about embedded design with microcontrollers in embedded systems course. These are the contents of my presentation. What are the things we are going to discuss in this session is, first we define the embedded systems. After that, embedded system applications, where it is used, what are the practical examples of embedded systems. After that, we are going to discuss about various aspects involved in hardware design. After that, various architectures such as Swan, Newman and Harvard architecture involved in embedded systems, and then microcontrollers architectures which are related with embedded systems designs, and then PIC microcontrollers as its different families with advantages and disadvantages, and then pin configuration of PIC microcontroller, and finally we'll discuss about the software design involved in embedded system process. These are my references. These are the textbooks of your course. So first we start with the embedded system definition. What is embedded system? Embedded system is a system whose principal functions are controlled by a computer embedded within it. So in a embedded system, a software is integrated inside the hardware. We are writing the coding for a particular application. After that, that coding is embedded within a chip. That is known as a embedded system. What are the applications is, by integrating these softwares in a chip, make it as a real-time system for solving the practical applications. So these are all the various examples of embedded systems. So GPS system is there, and then say a simple digital watch, and then a video audio player, and then traffic light, medical application, robotics, and then automated cars, then washing machines, everywhere. So what are the things involved with this? These systems using sensors to measure a practical phenomenon or real-time phenomenon. After that, based on the real-time input, the system takes some decisions with the help of the code integrated within it. That is the common thing in all these applications. For example, in the maps, it's get the position values, and then it's interacted with the location map. It shows what are the traffic is there, everything. In a digital watch, it's related with the time also. And then your music player, you are accessing the memory, and then you are playing the songs. The code for playing the songs is written within the chip itself, so it can be used as a real-time device. Traffic light controller, it is depending upon the timing related circuits are there. Based on this timing related circuits, it decided whether it is green or red or yellow. So medical applications are high-end devices, so it can be used in a simple watch to a high-end medical application, mobile phones, everything. So this is the practical applications, not only limited with these applications, it is used in various numerous applications. So this is the part of a embedded system design. So major design is categorized into two sections. The first one is hardware section, and the second one is software section. In the hardware sections, we are discussing about what are the input devices used, output devices used, in which pins are used as input pins, and what are the pins are used as output pins, and what are the interrupts are used. Everything we are deciding in this hardware design part. And then in the software design part, the coding part, it is a coding part. For solving a particular application, we are writing a coding. So what are the things, what are the time delays there, what are the loop functions are there, everything is decided in this hardware. A final embedded product is the combination of this hardware as well as the software. So you are integrating the application software into this hardware. So first start with the hardware design. So what is the first key factor for this hardware design is choosing a right microcontroller for application. So microcontroller is the heart of our embedded systems. So we need to choose a proper microcontroller to solve a particular application. And then what are the criteria for choosing this microcontroller is the microcontroller has how many pins, IO ports, and then serial communication modules, peripherals. Peripherals are timer, what is the timer IC is used, what is the ADC, analog to digital convert, pulse width modulation, etc. What is the purpose of this timer is in real-time application. For example, in a traffic light system, you need to enable a light for a particular period, time period. How the microcontroller know whether the light is enabled by a particular time period? So for this purpose, the inbuilt timer will help. And then what is the purpose of this analog to digital converter, ADC, is all the real time, most of all the real time inputs are in analog in nature. So we need to convert this analog inputs into a digital input, which is processed by a microprocessor or microcontroller. So we need to convert this into digital form. For that purpose, we are using analog to digital converter. So this is also a key factor for choosing the microcontroller. What is how many bits of this analog to digital controller is used, 8 bit, whether it is 8 bit, whether it is 16 bit, like that. And then pulse width modulation. A practical example for this is, suppose you want to control a high speed motors, we are using this pulse width modulation. The width of a pulse is related with the time period. So all of us know about this relation between the frequency and then time period. Time period is inversely proportional to the frequency. If the frequency is increases, means the time period is decreases. So by varying the time period, we can change, we can control a high frequency motors. Not only high frequency motors, it is used in very many applications which are related with a pulse time period. And then the third one, the fourth one, the memory requirements. It is also very important. So depending upon the application, the code's memory sizes varies. For a real-time application which has more array functions, which has more input functions, require a more memory. So you need to choose a microcontroller according to this. So memory requirement is a very, very important factor. And then processing speed, it is related with the microcontroller's clock frequency. So the processing speed is related with the execution time required to solve a particular coding. If the processor has high processing speed, means it requires very less time to execute a code. So processing speed is very important in terms of a real-time applications. And what is the power requirements? Also a factor. So we need to use microcontrollers which require less power consumption also. So these are the criteria for choosing a microcontroller. If you are choosing a microcontroller of for an embedded system, means half of our work is over. These are the hardware elements of embedded system. So first, the embedded system communicated with the external world through the input-output ports. So the input-output ports are important. These are used as a entrance for our embedded system. So the system is communicated with the external world through this input output. After that, the data received from the input IO port is processed by the CPU, central processing unit of an embedded system. What is the central processing unit? Central processing unit is the combination of arithmetic and logic unit and control unit. ALU is arithmetic logic unit is known as ALU. It's a short form of this one. So ALU means arithmetic and logic unit is related with the arithmetic operations and logical operations of a microcontroller. Arithmetic operations such as addition, subtraction, like this, and then logical operation and or XOR. So this arithmetic logic unit is responsible for doing this, and the control unit is responsible for controlling the timings signals and then other control signals, read, write, then its control signals are there. It's responsible for them. So CP is the combination of both arithmetic and logic unit and then control unit. And then your central processing unit, CPUs, can access the memory. Normally two type of memory is there, program memory and data memory. The program memory is also known as a code memory. Your application code is stored in this program memory, and the data related with this is stored in the data memory. So these are the fundamental architectures Von Neumann and Harvard architecture. These are the fundamental architecture used in many embedded systems. So first we know what is this Swan Newman architecture, and then what is Harvard architecture. Then only we can differentiate. So first we can see here in Von Neumann machine, a same memory is used for both data and code. So the data and code can be stored in a same memory. There is no separate memory for data and code. So the central processing unit access this data plus code which is stored in a memory location. So we have the bus. You can see here a data bus is there, that is bidirectional, and the address bus is also there, that is unidirectional. Why the data bus is bidirectional means it has two operations, read and write. So in the read means the processor read the instructions from memory. Write means it write its output to the memory. So first operation is memory to processor. The second one is processor to memory. So to support this, the data bus is bidirectional. The address bus is unidirectional because the processor access the memory location. So for this purpose, it is unidirectional only. So then your CPU communicated with the IO devices through this data bus. Here also we are performing a read as well as write operation. So the bus is bidirectional. In the right hand side, that is Harvard machine, Harvard University, name of Harvard University. So it has a separate memory for program as well as data. You can see it, program memory is there and data memory is there. It is a separated memory. So what is the thing we are going to do is, in the program memory, we are writing our application software. The data memory, it can be accessed data through this data memory. What is the purpose? In the program memory, not only application software is stored. Along with the application software, we need to store the constant data also inside this program memory. What is the purpose? We are using this constant data. For example, we are using a microcontroller based motor control system. In the systems, we can use a lookup tables. The lookup table is the constant data. So the constant data can also be stored in the program memory. Every time we cannot give the input of this lookup table. So the input can be stored for as a file inside a program memory also, because it's a constant data. It can be accessed every time. So this can be stored in the program memory, because program memory is a read-only memory. So we can store a fixed data only in this program memory along with your code. This is the difference between a Von Neumann machine and then Harvard machine. So what is the memory is the key factor. So these are the differences. Other points are there. How the Von Neumann architecture is different from a Harvard architecture. So Von Neumann architecture is a theoretical design based on the stored program computer concept. Harvard architecture, compared with this Von Neumann architecture, it is a modern computer architecture based on the hardware model, Harvard University model. It has only one bus. Von Neumann architecture has only one bus that is used for both instruction fetches and data transfers. We already point out this point. In Harvard architecture, it has separate memory space for instructions as well as data, which make it possible to access each of the memory systems simultaneously. So we can access the code memory as well as data memory simultaneously. In Von Neumann architecture, the processing unit would require 2 clock cycles to complete an instruction. Here, in Harvard architecture, the processing unit can complete an instruction in 1 cycle if appropriate pipelining plans have been set. So it is purely depending upon the pipelining process. In Von Neumann architecture, it is usually used to the desktop computers, notebooks, high performance computers to workstations. So a higher end processors, it is a general purpose. A higher end processors prefer Harvard architecture. Okay, that is a higher end processors used for digital signal processing, which process a real time speech signals and then other image, everything. There is a real-time signals. This prefers a Harvard architecture. In von Neumann architecture, instructions and data use the same bus. And Harvard architecture, it is a complex kind of architecture because it employs two buses for instruction and data. A factor makes development of the control unit comparatively more expensive because we need to process speech signals and image signals, so the cost is high. So it is an expensive one. So we need to choose in the real environment applications, we need to prefer a microcontrollers. Why we are preferring the microcontrollers means, suppose we go for a application specific, then we are using a microcontrollers. How a microcontroller is different from a typical microprocessor, so we need to discuss why a microcontroller is preferred in real-time application, how it is different from a microprocessor, so we'll discuss. So first, as in CPU, CPU, central processing unit, in microcontroller, specific purpose CPU. So because we are using a microcontroller for a specific applications, so the central processing unit is, we are choosing the microcontroller with a central processing unit which is suitable for the particular application only. In contrast with this, for a microprocessor, it is a general purpose. For example, our computers, we are not using it for a specific application. We are using it for a multiple application. So we need to choose a microprocessor for a general purpose application. If your application is specific means, we need to choose a microcontroller. And then speed, how a microcontroller, it is used for a specific application only. So the speed is low. It is a slower one. And then compared with this, microprocessor is the faster one. And then components. In a microcontroller means it is a single chip computer. So along with our CPU, other devices, other peripherals, ADC, everything is integrated inside a chip. So all devices and peripherals are integrated inside the chip. In microprocessor, components can be outside the processor. Other than the CPU, central processing unit, other peripherals and memory is placing outside the processor. So this is the major fundamental difference between a microprocessor and microcontroller. And the Boolean functions, it supports, microcontroller supports a Boolean functions, microprocessor doesn't support the Boolean functions. And then CPU registers. Microcontrollers are used for a specific applications only, so it can be accessed, faster accessing of CPU registers. And then need to more time to access a CPU registers because of a multi-purpose and then general purpose. We are using it for many applications. So CPU register accessing is comparatively slower. And then usage. It is used for a application specific. So it's a real-time application. And then in microprocessors, it is used in our computers, laptops, everything. And then real-time operating systems. So it supports real-time operating system. Microprocessor also supported. And then it supports more than one OS, microprocessor supported because it's a general purpose. So it supports more than one OS, everything. Compared with this, a microcontroller, it is lower. A bitwise operation is supported by a microcontroller, but the microprocessor does not support all bitwise operations. So bitwise operation is specifically used for application specific. You have a port, the port has multiple number of pins. Suppose you want to enable a port, we can use a port enabled instruction. Similarly, the port has multiple pins. Suppose we want to enable a specific pin means we are using a bitwise operation, a microcontroller support it. And then compared with microprocessor, the hardware complexity is very simple in microcontroller, but in microprocessor it is complex because it is used for multiple applications, so it is complex. And then the cost is also low for a microcontroller, and then it is expensive for a microprocessor. The same reason, because it is used for multiple applications. It is a general purpose. We can use it for many applications, so it is also expensive also. And then multitasking is supported by a microprocessor, but a microcontroller does not always support the multitasking. So examples for microcontrollers, these are the examples. 8051 is there, PIC microcontroller is there, And then here a microprocessors, it is a Pentium processor is a great example for a microprocessor. So we need to choose a microcontroller for a specific application. So this is the architecture of a microcontroller. So power unit is there. Normally it is powered by a 5-volt supply. And then program memory is there, data memory is there. Program memory is used to store our application code and a constant data. And data memory is used to store variable data. And then how the microcontroller is communicated with the external world through peripheral devices. And then these peripheral devices are allocated, and then it supports analog IO input output as well as a digital input output also. Along with this, a fundamental features, a counters and timers is also integrated within the chip. This is a different, in this way it is different from a microprocessor. In the microprocessor, it is only a central processing unit is integrated in a chip. Here, along with the CPU, the other counters, timers, ADCs, related things also integrated within the chip because it is used for a application specific. So it is enabled by a clock frequency. The processing speed of a microcontroller is always depending upon the clock frequency. The clock frequency is decided by the crystal oscillator used, the oscillator used. We are connecting an oscillator to this microcontroller, and then the clock frequency is purely depending upon the micro oscillator frequency, and the processor's operating speed is depending upon the clock frequency. So it is very important to choose a particular oscillator for a microcontroller. For it is very important. So the microcontroller is uh, enabled or disabled for it in real-time applications. We have interrupts are there. The external devices send a interrupt signal. Then the processor or decide whether it can be processed or whether it can be masked or other things. So these are the overview of microcontroller architecture. So some popular microcontrollers are used. Intel 8051, it is a mostly used 8-bit microcontroller, and then peripheral interface controller developed by Microchip also one of the things. It is used in many real-time applications. Motorola and Zilog also developed their products. So PIC microcontroller, peripheral interface controller, is mostly used in many real-time applications because of its IO devices handling ability and then timer and other related functions. It is preferred. So we will go further to explain about the details of this peripheral interface controller. You can see the comparison of different controllers based on its size. To compare the size of the controller, we can place a coin here. So you can see from left to right, the first one is PIC controller. The PICs, the many versions are there. 12F version, this is 16F, and then 16C. F means it's the flash memory, and then this 16C72, and then Motorola, other processors are there. You can see the size of the chip is varies. So as normally a small size chips are preferred. So compare compare the size of this chip with the coil is very less. So small size of a chip is preferred because it can be suitable for a compact design. So your device size is depending upon your controller size. So we need to choose a smallest one in terms of compact design as well as a power consumption. What are the things are related with choosing this smallest means? Two things are there: high density and then high frequency problem is there. Suppose I want to increase the operating frequency of a particular device means the chip size should be small. So the chip size should be small. But the smaller chip is related with the design technology. So VLSI is there, a lot of technologies are there. So suppose I want to design a high operating frequency device means it should be a compact in size, so you need to wait. Because VLSI technology support, according to Moore's law, a transistor size is doubled. Okay. So we need to wait for a particular period to incorporate a more number of transistors inside a chip. Otherwise, it is difficult to design a high frequency device. So wherever, what is the thing is depending is to design a high speed device, the size should be less. To select a high speed device, you need to wait to incorporate all more number of transistors inside the chip. So it is dependent. That is the reason in the earlier days we have a huge size chips. Now it is very smaller in size. What is the reason is the design technology is increases. It accommodates more number of transistors inside the chip. So the chip size is reduced. That is the thing is there. So PIC microcontrollers, it is the mostly available microcontrollers, mostly used microcontrollers also in many applications. What are the features for choosing this PIC microcontrollers? It's the cost. First one, because the real-time applications we are using, the product cost is also a matter. So the cost should be less. So it's a low cost, and then self-contained. So memory and other input ports are integrated within the chip itself. So this is a self-contained controller. And then it follows a 8-bit Harvard architecture. We already discussed about the Harvard architecture, and then it follows a Harvard architecture. And the pipelined one, what's the advantage of this pipelining is it can be multiple instructions can be overlapped during execution. Here in the right hand side, we can see the pipelined implementation and a non-pipelined implementation. You can see instruction 1, instruction 2, and instruction 3 are there. So 3 instructions are there. In a non-pipelined implementation, these instructions are executed one by one. You can see instruction 1 is there, instruction 2 is there, after that instruction 3. First it execute the first instruction 1, after completing the process only it go for a instruction 2, and then it go for instruction 3. Here you can see it is multiple instructions are overlapped. Instruction 1, instruction 2, and instruction 3. 4 processes are there: fetch, decoding, execution, and write back. While decoding a second instruction, while decoding the second instruction, it can be fetched as instruction number 3. So it is a multiple instructions are overlapped. There is a major advantage of a pipelined implementation. Your PIC microcontrollers follows a pipelined implementation. So it can be reduce the time of execution. So it can be suitable for a real time applications. This is a comparison of PIC architecture. Various PIC architectures are there. So let us start with the PIC 12CX. What is the stack size is very important. The stack size is 2 for this PIC CX. What is the instruction word size is 12 or 14-bit. Number of instructions in instruction set is 32 instructions. It doesn't support any interrupt vector. Compared with this 12CX, 16, this has a 2 stock size and instruction word size is 12-bit. It also having a 33 number of instructions in its instruction set. It also doesn't support a interrupt vector. From 16C, the stack size is 8, instruction word size is 14-bit. Number of instructions is compared with it is more. It is 35 number of instructions. It also support a 1 interrupt vector. So 16 big 17 version, the stack size is increased double compared with the 16 version, that is 16 stack size, and the instruction word size is also enlarged. It is 16-bit. It can be support 58 number of instructions, and it can support 4 interrupt vectors also. PIC 18 is the advanced one compared with this PIC 17. Okay, the stock size is improved, stack size is improved double. So it is 32. The instruction word size is 16-bit, and the number of instructions is 75. Number of instructions is 75. The number of interrupt vectors supported by this 18 series is 2. So your controller communicated with the connected devices through an interrupt vector. The interrupt signal is sent by the devices. The controller decides whether the interrupt can be processed or the interrupt can be masked, everything. Some signals, the hardware failure related signals are non-masked. Okay, so the interrupt vectors plays a very important role. So when the microcontroller receives the interrupt signal from the device connector, it will go to a particular location. The address is indicated by this interrupt vectors. So it is very important role is there for interrupted vectors and interrupt signal in a practical microcontroller based designs. So these are the pin, various pins used in PIC microcontroller. The next slide will discuss about the function of each pin. We can see here, here is a 40 pins. 40 pins is there. So input of various input output pins are there, and then supply and then memory clear pins are there. We can explain the function of each and every pin in the next slide. So first, the oscillator pin. You can see pin number 13 and pin number 14. You can see OSC. This is the abbreviation of oscillator. So you need to connect a oscillator across this. The oscillator frequency is related with the clock frequency, and the clock frequency is related with the execution speed of an instruction. So it is very important to choose a particular oscillator. So you need to connect the oscillators to the microcontrollers through this pin number 13 and pin number 14. And then this one, the memory clear is there. It's a pin number 1. And then these are all pin number 2 to pin number 7. These are all related with this port A. Port A is a bidirectional IO port. So these are all the pins of this one. So RA0 can also be analog input. One is also analog input. RA2 can also be analog input 2 or negative analog reference voltage. RA3 is also can be input 3 or positive analog reference, and then 5 can also be analog input 4 or slave select for the synchronous. These are all related with the port A. Similarly, the B not to, here you can see B0 to B7 is related with a port B. B0 to B7 is related with the port B. This can be used as a external interrupt pin also. You can RB0 is there. This is INT is there. INT means is the interrupt. It can be acted as an external interrupt also. What is the thing? The processors design, you need to, the microcontrollers design, you need to concentrate to this. What are the ports are there? What are the ports are used as IO devices input? And then what are the pin frequency related things are there? Clock frequency generator and then clock frequency output. What are the clock input is there? What is the clock output is there? So because every execution time is depending upon purely depending upon this one. So we need to concentrate about more. In PIC microcontrollers, a crystal oscillator is connected. So the clock output is 1/4 frequency of the oscillator 1. So we are choosing the oscillator of 4 megahertz. The frequency is 1 megahertz. So normally it is choosing up to 20 megahertz. So it can be supported 4 megahertz according to this. So the instruction cycle is depending upon this oscillator connected and this the frequency of an oscillator used. So these are all the various pins of PIC microcontroller. So they already discussed the oscillator selection about. So suitable oscillator is depending upon the required processing speed. What is this required processing speed is depending upon the code size. We are writing a larger length of codes required a larger execution time. So we need to choose a application. We need to choose the oscillator according to this application. So application has a lengther codes requires a higher frequencies. So the required timing is precision because these are all the real-time applications. The response is within it can be generated within the bounded time. So we need to concentrate about the processing speed also. So this processing speed is depending upon the code memory size. The code memory size is large means we need to choose a higher oscillator frequency. So this is important. So this is the memory organization of thing. What is the thing we already discussed about the stack? Okay, and the fundamental difference between the stack architecture and then queue is different. In the queue, it is first in, first out. That in a stack, it is last in, first out. So program counter is there. The program counter is related with this. What is the role of this program counter? Is the program counter is it has the address of next instruction to be executed. While executing the instruction, the program counter value is incremented automatically to the next value. Then only the microcontroller know this is the next instruction. Otherwise, it is difficult. So the microcontroller knows what is the next instruction with the help of the program address stored in the program counter, the higher order as well as a lower order stored. For the stacking purpose, we are using this stack. The concept is last in, first out. And then these are all the interrupt vectors all there, because the external devices send the interrupt signal to the microcontroller. So then according to the interrupt signal, the controller can access the particular location, memory locations. Here this is 000, 004, like that. According to the interrupt signal, it can be access the location that is known as interrupt vectors. So these are the memory. On-chip memory sizes increases. We can get the layers, more layers when the memory is increases. So for a 2K, it is only one. For when I'm implementing this 4K, one more thing, and then 6K, the address we can increases, and 8K this increases. So when I'm increasing the on-chip memory, the advantage of on-chip memory is the accessing time is very less for an on-chip memory, but we need to pay the penalty. The cost is also increases. That's the thing here. That is a very important thing here. Off-chip memories are cheaper, but the accessing time is more. Suppose I want to access a data from an on-chip memory, means the accessing time is very less. It is a quicker one. But suppose I'm accessing the data from the external devices or external memory, the accessing time is more. But the external memory is cheaper one compared with the on-chip memory. The on-chip memory is the costliest one. So we can decide the on-chip memory also based on the application. So we need to select a particular microcontroller with this specific memory depending upon the application also. Your application is the simplest one, means we can choose a microcontroller with a less number of on-chip memory. Otherwise, we need to go for a larger on-chip memory. The final one, after the hardware modules is finished, you need to concentrate about a software design also. The software design is totally depending upon how to develop a application code for a specific real-time application. So you need to write the code to solve a real-time application. After that, we need to integrate, you need to embed the code in the on-chip. That is the process. That is the finalized one. So what are the things are going? First of all, you need to write a coding for the particular application. So we have two choices. The first one is assembly language, and the second one is high level language. The assembly language, it is an intermediate between a human language and machine language. Many things are there. 8051 assembly language is there, and then what other thing is, it is not closer to a human language. In a high level language is closer to a human language. It has very less, it has assembly language has a specific instruction. So it is purely hardware dependent. High level languages, it is independent of a hardware. The program written for 8051 is not suitable for other microprocessor or microcontroller. Program written for in the earlier versions, 8085 is there, 8086 is there. The program for 8085 is not applicable for 8086. What is the reason is, it is purely depending upon the hardware. So to write a assembly language, the developer must have a hardware knowledge. What is the memory things? What is the memory? What are the vectors are there? And what are the IO ports are there? What is the specific pin used for that? Everything we need to decide. For example, the 8085 microprocessor is there, 8086 microprocessor is there. The first one is doesn't support a direct multiplication. So we cannot directly use a direct multiplication instruction for that. So the programmer must know about that, the 8085 won't support a direct multiplication. So we need to write a coding in terms of repeated addition. That is the thing. So hardware knowledge is very essential for a assembly language program. Very, very essential. Compared with this high level languages, it is less preferred with respect to this assembly language programming. C programming is the example. While writing the C program, you don't much worried about that system. What is the system it is used? Whether it is used in this system, Pentium 4, or then other versions. Whether it is used in higher end, we cannot decide about this. So we cannot think much more about that. What is the thing we are deciding is what are the number of instructions is there, execution cycles, and library functions. These are the things we are concentrating. We are concentrating very less about the hardware compared with the assembly language. It is pure assembly language. We are concentrating more on the hardware. And then assembler is there, compiler is there. What is the thing is, you are writing the program. It can be accessed, it can be executed by the machine. So you need to convert it into a machine code. So for that purpose, in terms of assemblers is used in assembly language. What is the role of assembler is? The assembler convert assembly language into a machine code. For a high level language, we are using a compilers. The compilers convert high-level programming languages into a machine code, because the machine code is so the machine can access the machine code only. So we need to convert it before we can be developed a execution file. You need to convert it. Then only it can be executed by a processor or controller. So this is the high-level language is there. So compiler convert it into a machine code. So this is the common thing for assembly language and machine language. Whether it is assembly language or high-level language, it can be converted it into a machine code to access by the controller. So it is a very essential step. After that, the device programmer is there. With the help of a device programmer, it can be stored as in a program memory. So your code is stored in a program memory, and it can be accessed by any applications. Okay, so any application for accessing real-time applications, we need to access this code only. For that purpose, it is stored in a program memory, which is read-only memory. Thank you. So this end of these things, I summarize everything. So in a embedded system designs, you see microcontrollers is our topic. We discussed about what is an embedded system. So a system integrated in a hardware. You are integrated a application code inside the hardware, that is known as an embedded system. So we are discussing about various aspects of embedded systems. We are discussing about Von Neumann architecture and Harvard architecture. The first one is the architecture with the separate things, separate program memory and code memory, and the other things also we discussed. What are the other aspects of the Von Neumann and Harvard architecture also we discussed, and we discussed about a microprocessor, which is a single chip CPU, and a microcontroller, which is a single chip computer also we discussed, and then various advantages and disadvantages of a microprocessor and microcontroller also discussed. Then we related the processor size, microcontroller size with real-time applications. So smaller size of controllers are preferred for compact devices. And then we discussed about the PIC microcontroller families. We compare the various PIC microcontrollers and what are the microcontrollers are used and suitable for a real-time applications also we discussed. Finally, we discussed about the software design and various aspects of a software design, like our assembly language programming and high-level programming, and then why assembly language programming is used and why high-level language is used, how does high-level programming or assembly language programming is incorporated inside the chip also discussed. Thank you.